All right, here we are with the last section for Chapter 4, Molecular Structure and Polarity. You can see once again the learning objectives have been listed for you. So here we're going to talk about valence shell electron pair repulsion, VSEPR theory. You can see that as one of the learning objectives that has been listed. So VSEPR theory allows us to predict molecular structures and with that, understand bond angles around the central atom based on the number of bonded pairs versus lone pairs. Now that we can draw Lewis structures, we should be comfortable identifying lone pairs and bonded pairs around a central atom. The idea here is that we make these predictions on the shape or the geometry of the molecules based on the idea that we understand the arrangement is going to try to minimize those repulsions between these electron pairs by maximizing the distance between them. Just to think about the name of the theory, valence shell. So as you have seen, we're talking about valence electrons that are either lone pairs around the central atom or bonded pairs. Electron pair, okay, like I just mentioned a second ago, they're all pairs. And since we're dealing with electrons, electron pair repulsion. Electrons are all negatively charged particles. So again, the idea here is that these electrons are going to attempt to space themselves out in 3 dimensions as far away from as possible from one another. And because of that concept, to minimize those repulsions, because of that concept, we can predict what their geometry will be. So you can see here, this table predict the shapes of molecules. So a couple things here that we want to identify and talk about as we consider VSEPR theory. Okay, so I'm going to jump down here to actually electron groups on central atom 3 here to start, because there's a couple things I want to point out. Okay, so you can see the electron group shape. Now, depending on the resource, how they title these different categories may differ. In this particular example, it refers to electron group shape here and molecular shape here. Just so there's no confusion, your textbook would refer to this first category as electron pair geometry, and this second category as molecular structure. Again, depending on the textbook or the resource, what they title these 2 categories may differ. The concept is the same, and that is that for the first category here, electron pair geometry, we are just talking about overall pairs of electrons around the central atom. So this includes both bonded pairs and lone pairs. The molecular shape is going to make a distinction between bonded pairs versus bonded pairs and lone pairs. So as we can see here in this first example, when I have 3 pairs of electrons around the central atom, I have a possibility where all 3 of those could be bonded pairs, leaving me 0 lone pairs, and I could have 2 bonded pairs and 1 lone pair. So the overall electron pair geometry, or what this table refers to as electron group shape, that is going to be trigonal planar for both categories. But then the distinction is, based on how many lone pairs there are, that means the shape is going to change. It's either going to be trigonal planar, 3 and 0, or bent, 2 and 1. So the idea here and why this changes is because if we take a look all the way over here on the right side of this, when I add a lone pair of electrons, that pair is no longer shared between 2 atoms, so it becomes a pretty negatively charged region around the central atom. And the effect it's going to have, it's going to change the shape. It's going to bend, in this case, those bonded pairs of electrons even further away from one another. So the bond angle is going to change, and therefore the shape is going to change. Now, we don't necessarily need to know the specifics of the bond angle, but we should definitely know that in each circumstance, as you can see here, my bond angles for a molecular structure or molecular shape that has 3 bonded pairs and 0 lone pairs is 120 degrees. We should understand that if I remove a bonded pair and replace it with a lone pair, what that is going to do is it's going to decrease my bond angle. So as you can see here, it's just written as less than 120 degrees. Let's take a look at our next category, 4 electron pairs. Okay, so you can see here the electron pair geometry is referred to as tetrahedral, 4 pairs around the central atom, and then I can have 3 different possible molecular shapes or molecular structures. I have the 4-0 possibility, which would still be called tetrahedral. I have the 3 bonded pairs, 1 lone pair possibility, which is now called trigonal pyramid. And I have the 2 bonded pairs, 2 lone pairs, which is referred to as bent. Again, take a look at the bond angles here. The 4-0 tetrahedral is 109.5. And then as I remove bonds and replace with lone pairs, the bond angle is going to become smaller. So for those next 2 categories, I should understand that it's going to be less than 109.5. Next, we have a couple categories that we haven't spent a lot of time talking about yet because they represent expanded octets. So central atoms that have more than 4 pairs of electrons around them, 5 or 6. Okay, so obviously the more pairs of electrons I put around the central atom, the greater possibility I have for different molecular shapes. But again, 5 and 6 is my electron pairs. And then we can remove bonded pairs and replace them with lone pairs. And you can see the different shapes here from trigonal bipyramid, seesaw, T-shaped, and linear. And then for the octahedral, 6 and 0, we get a couple additional ones. We usually don't go beyond 4 and 2, that square planar model. Just last thing I want to point out here, this table is available to you. You should start to memorize these different shapes, both the electron group shape and then the particular molecular shape and the bond angles that go with them. Last thing I'll just point out here is there's a column here for hybridization, and this is not a concept that we have covered yet, but we will be covering soon enough. So don't worry about that just yet. We'll come back to that in future sections. Okay, the last thing for us to cover in this section is polarity. So polarity means that I have regions of charge. Now, we can look at it both as bond polarity and as molecular polarity. So let's just think for a second. When I have ions and ionic charges, so if I had the sodium cation and the chlorine anion, we understand that these charges accumulate because of the idea of losing or gaining electrons. So sodium, with its 1 valence electron, is looking to give that electron away to form a bond. So that's where we get the +1 cation, whereas chlorine, with its 7 valence electrons, is looking to gain an electron, making it a -1 charge. So that's where these charges come from. We've done a lot of work with those with ionic compounds. Now, the same thing doesn't quite happen with molecules or covalently bonded compounds, but there is still some charge that is generated, and that's due to an unequal sharing of electrons. So in the example here of the CO2, the bond between the carbon and the oxygen is not shared equally. Okay, this is due to a difference in electronegativity. There's that term again that we have been working with. So as you recall, this is an atom's attraction to electrons in a bond. So because oxygen is more electronegative than carbon, it is going to pull this shared pair closer to itself. Now, we're not going to truly be in a situation of gaining and losing electrons, but we are going to generate some charge here. Because this shared pair is pulled closer to the oxygen, we say it has a partial negative charge. And because the carbon is losing, or that shared pair is being pulled further away from it, we refer to that as a partial positive charge. So we have this idea of bond polarity that occurs due to differences in electronegativity. We also indicate this by drawing a dipole, and that just is an arrow that looks like this, that originates in the positively charged end of a bond and points to the negatively charged end, in this case partial positive and partial negative. You can see here that we draw it purposely like this so as to look like a plus sign. All right, so as you can see over here in the CO2 example, we have two polar bonds. In both cases, the oxygen is pulling that shared pair that they're sharing with the carbon away from the carbon and closer to itself. So CO2 has bond polarity, but it is not polar overall as a molecule. And the reason being is that those two dipoles, as you see here pointing in opposite directions, cancel each other out. So overall, this molecule has a dipole moment of 0. I cannot indicate or draw in this molecule here where I would have a region of negative and a region of positive in the molecule as a whole. So molecular polarity is affected by both bond polarity and the geometry of the molecule. You can see what I'm talking about here as we look at this water molecule. So in this case, both of these bonds are polar, just like in our first example, where the shared pair is pulled closer to the oxygen, creating a partial negative here and a partial positive here in this bond moment. Same thing would be happening here in this bond moment. Additionally, you may recall that this oxygen is also going to have lone pairs. So we'll additionally have a couple, just erase this for a second. Additionally, we're going to have a couple lone pairs of electrons sitting on the oxygen as well. So even though the bond polarities cancel each other out in the first molecule, that's not going to quite happen here because they're both getting pulled towards the oxygen. Additionally, we get this bent shape due to the lone pairs that are sitting on the oxygen. And so overall as a molecule here, you can see that I can indicate where I would have a region of negative and a region of positive in this molecule. So up here overall, I'm going to have a region of negative, and then down here in between the hydrogens, I'm going to have that region of positive. And you can see that's how we've drawn that dipole moment. Sometimes they would draw this dipole moment actually right through the oxygen, so that you may see it drawn for water like this, right like that. So let's look at a couple other examples real quick. Let me first think about CH4. So if I draw my Lewis structure, so that's the first step in this, being able to correctly draw a Lewis structure. If I were to draw my Lewis structure, and now we can also think about these as three-dimensional shapes, so I can think about drawing these a little more accurately by indicating that two of these hydrogens are in and out of the plane here of the paper or the screen. But anyway, you can see here that due to the symmetry in this molecule and no lone pairs on the central atom, and the fact that every atom connected to that central atom is the same, that even if I have a polar bond there between the carbon and the hydrogen, they would all cancel each other out. And so I would not be able to identify a region of positive and a region of negative in this particular molecule. So I would identify this molecule as non-polar. Whereas if I had something like NH3, I would get I would draw my structure like this. And now you can see, due to the fact that I have a lone pair of electrons sitting here, I am going to have a region of positive and a region of negative. And my dipole moment is going to be drawn just like this. Or up here by my lone pairs of electrons, I'm going to have that partial negative, and down here in the middle of my hydrogens, I'm going to have that partial positive. That wraps up our last section here. Now that we know how to draw Lewis structures, once we have a Lewis structure and we can look at that structure to determine how many bonded pairs of electrons and lone pairs of electrons we have, we can identify what the molecular geometry would be, both in terms of overall electron geometry and also the molecular shape based on bonded versus lone pairs of electrons. Once I can do that, I can also identify whether or not I would have a polar molecule based on the bond polarity and the molecular shape. Okay, one of the key points to look for when considering molecular polarity is whether or not there are lone pairs of electrons sitting on that central atom. Well, let's get some practice in and get comfortable with both of our identifying our shapes and bond angles, and also whether or not we have a polar molecule.